All right, so now we're going to get to our final part of the aromaticity chapter, which is to kind of use the consequence of aromaticity to understand reactivity. And we're going to start with the simplest reaction possible one we know before the next chapter, which is learn a lot of new ones that we did not know. So, makes sense, right? Acid-base, one of the simplest reactions we could do. We're going to see how it affects the acidity or basicity when a molecule has that property of either being aromatic, possibly being anti-aromatic, changing its aromaticity characteristics in any way. So that's the goal. So here's a few examples that can help us get there. For example, compare these two somewhat similar looking molecules. So here's pyrrole, and this is pyrrolidine. Pyrrolidine. Okay. Who's a stronger base? So in other words, there's a lone pair there. We know amines can act as bases using that lone pair, right? So we know this about amines. We have this simple reaction going on. If there's an H, a proton available, and we grab it to let amines act as a base. This is the acid. Voila, here's our acid-base reaction. The lone pair is gone. It's part of the bond, the new sigma bond to that H that it took. All right, so if we track the new H, because remember we had those two old H's on there, that's the new one. It gained an H. So it's a conjugate acid of the base. So when we are solving acid-base problems and predicting acidity or basicity, and the question is who's the stronger base, you always draw the conjugate acid or base of whatever it's doing. So if you're asking which is the acid, draw the conjugate base, because you want to see what is the effect of making it be an acid, right? What is the effect of making one of these be a base? Clearly, they're going to have a different sort of reaction to that because we're varying the R group here. They're both amines of sorts, right? They're a heterocycle with a nitrogen that the lone pair is going to be tied up now, making a sigma bond. Which one of these does not want to tie up its lone pair? So draw out that conjugate acid always. So if this is a base and this is a base, we're going to draw out the conjugate acid. If you were asking who is the stronger acid, we would draw out the conjugate base. Okay, so let's zoom in here. And then we compare which conjugate acid's worse to form. Aha, that'll tell you which base is more reluctant, hence weaker, right? So what happens when we make our base? So turn into conjugate acid. To let that act as a base, it takes that H. So drawing the very simple mechanism here. Not even defining what the acid is. All we know is it's a proton source. Remember, the lone pair is now gone in both cases. New H is added, gives us a positive charge on N. New H is added, gives us a positive charge on N. So I'll circle the H we added. Doesn't matter which one, really. Okay, so we can all get to that point, I hope. Now think about this chapter. We're going to ask, and about when we ask this following question, which conjugate acid is the least stable? Which one did we not want to form? Well, remember we go through CARIO and all of that, right? Aromaticity is a whole nother aspect of CARIO because if you think about resonance, that happens when you have conjugation. But aromaticity is even more important than conjugation. So let's see if we can get to that. Keep it simple. So since this is a chapter on aromaticity and we have a ring system that's conjugated here, look at 2, 4, 6 pi electrons, it's an aromatic. It's one of the aromatic examples we looked at. Notice that this is not an issue. You can't even evaluate its aromaticity. It doesn't qualify, it doesn't pass the first test. So this is non-aromatic. Okay, now let's see what happens to the product. It's aromatic because it has 2, 4, 6 pi electrons. But notice this lone pair is gone after this reaction. We have 4 pi electrons, and we cannot delocalize. We cannot have resonance. So we've turned it from aromatic. We have 4 pi electrons, but it's not anti-aromatic because we can't delocalize it. We didn't pass the first test of aromaticity. So it's actually non-aromatic now. This was never aromatic to begin with, so there's no way it's going to become aromatic just because we were never conjugated to begin with. So we didn't add any extra conjugation. We actually lost any chance of that by taking away any electrons that would have been in the pi system. So there's no change in aromaticity there. Look what happened here, though. I'm going to write it in green. Aromatic to non-aromatic. We lost aromaticity. So what do you think that does? If we have, let's say we have one acid equivalent and we let it choose between these 2 bases, which base is more reactive? Which base is going to grab that one acid, that one proton that's available? Of these 2 molecules, this one is going to be very reluctant. That lone pair is not localized, it's delocalized, it's stabilized. It's not as electron rich there. It's not going to be as drawn to the proton compared to this one. This one reacts a lot faster because it's localized. That's an electron rich nitrogen, hence more basic. Right? So in other words, we went from stable to less stable. We went from comparable stability to comparable stability. So if we make a disfavored process happen by making an acid react, it's not going to want to do that. It's going to be a weaker base, right? So lost aromaticity, therefore weak base. It does not want to react with an acid. So it's a weak base. Let's look at another one and see if we can compare it to those 2. Pyridine. Now, I'm going to ask you to compare it to pyrrole because we've already seen that change with pyrrole. So versus this one, the one that lost aromaticity. Does the same fate happen to pyridine? Because remember, pyridine is another example of something that's aromatic. We say, and you might say, well, I've already learned if it's aromatic, it's going to be a weak base. Well, what if we have 2 aromatic systems? Is it really going to be a weak base? Actually, pyridine we use over the arrow regularly in organic 1 as a base. It's actually not a bad base. Why is it not a weak base when it's aromatic? You have to draw the conjugate acid. So let this be a base. Show how it reacts with a proton. Okay. Ask yourself, I started aromatic. Is my product, my conjugate acid, aromatic? Yeah, 6 pi electrons. Right? All right, in blue, since I had it in blue before. So what was different here? A lone pair grabbed an H, and it did not lose aromaticity, whereas a lone pair grabbed an H here, and it lost aromaticity. Well, this lone pair was part of the pi system. This lone pair was, and this is why we still need to know how to interpret hybridization. What orbital is that lone pair in? That nitrogen, if we did not look at these pi bonds, in other words, if it looked like this is an sp3 hybridized nitrogen over here. Oops. So that means it's using 4 sp3 hybrid orbitals, including where the lone pair sits. sp3 orbital. That lone pair, because it can be conjugated and have resonance with these nearby pi bonds, allylic pi bonds next to lone pair. Remember, they are no longer in a hybrid sp3 orbital. They have to be in a p orbital in order to participate in the conjugation and resonance. So this lone pair is actually in a p orbital. Where's this lone pair? Is it the reason we have resonance? No. The 6 pi electrons come from 2 pi, 2 pi, 2 pi. That lone pair doesn't provide any pi electrons, therefore it's not in a p orbital. It's still sp2 hybridized nitrogen, but it's using its p orbital for the pi bond. Therefore, that lone pair is actually in an sp2 orbital, not p orbital. That's why you don't disrupt any sort of aromaticity, because you're not taking it out of the pi system. The lone pair is not part of the pi system. So see that difference? When that nitrogen has a double bond to it, that changes its lone pair's role, right? There's no double bond to that nitrogen. So that lone pair has to provide the pi system by occupying a p orbital. Okay, I hope that clears that up, but we still haven't answered the question. Who would be more basic, pyridine or pyrrole? Pyrrole lost aromaticity, weak base. Pyridine stayed aromatic, so it does not hurt it to be a base. In other words, it doesn't lose a lot of stability. Therefore, it is a stronger base than pyrrole. Pyridine is a stronger base than pyrrole. Okay, so in summary, in addition to all this CARIO stuff we've done previously, remember CARIO? Charge. So if you look at, you draw your conjugate base or your conjugate acid whenever you're evaluating strength of acids and bases, and then you look at charge, aromaticity, atom, resonance, inductive effect, orbital. We're going to add resonance to that and aromaticity wrapped up in that. So aromaticity trumps the resonance. So you got to watch out for that. If you're comparing acidity or basicity to your starting material and you're trying to determine which relationship is true, if an aromatic ring is part of the game, if the product loses aromaticity, the starting material is less reactive. It doesn't want to react. So that would mean it would be a weaker acid or a weaker base, depending on what you were looking at. If the product aromaticity gains aromaticity, then that would actually be a reason for the starting material to want to react. So the example we just did, we were comparing cases where it either stayed the same or lost aromaticity. How can we visualize something actually gaining aromaticity so that it actually wants to undergo that reaction? That definitely can happen. So I'm doing another one here, another example for you, and that's where we'll end it. Okay, cyclopentadiene. Whenever I'm reading these word problems, as you might say, I draw out the structures as I go. Cyclopentane with 2 alkenes, cyclopentadiene, has an unusually low pKa of 16. Why cyclopentane has a pKa of 40? Huge difference. So which H is going to come off? So we're talking about the acid-base reactions. If we're talking about pKa, we're letting this be the acid. So we need to have a base. I'm not defining what it is, but either way, we have a base. So all of the H's on cyclopentene, there's one pi bond. So if we remember which protons we normally take off, we're not going to take off vinylic H's. So this is a vinylic H. So vinylic means it's on the pi bond. Those are not acidic. Allylic, which is adjacent to the pi bond, much more acidic. So these would be equivalent ones. Either one of those 4 would be equally acidic. Oops. Allylic, adjacent to pi bond, Those are acidic. Why? You'll see, you're going to have resonance, right? So we're going to find the allylic proton, since we're talking about a pi bond system, allylic proton, so any one of those. And here, vinylic, vinylic, vinylic H, vinylic H. There's our allylic H. Those are the ones we want to look for. One of those would come off. Okay, so here comes the base. Takes an allylic H off, leaves electrons behind. We're doing the opposite. We're doing an acid-base reaction where the organic substrate is losing the H instead of gaining the H. So take off that H and only the H, leave the electrons behind as a lone pair on the carbon. We get a carbanion. So since this is the acid, we're going to draw the conjugate base now. So that looks like lone pair here. We have one H left, which you don't have to draw if you don't want to. All right, now we see why the allylic H was a good one to pull off, because look how we have resonance, right? We could push the arrows down here or down here. So that's why we take off the allylic as opposed to vinylic H's. Let's do that again. Let's show our arrow. Take that off, leave that here. Consequence of that, we only have one H left over. Huge difference in pKa. Look, you might say, oh, there's more resonance, but it's actually a very big difference. What's going on there? So remember this chapter's name? Aromaticity. So let's label the aromatic properties. Whenever you have a ring and conjugation, watch out for that, okay? So right now we have a ring system when we started, but it was non-aromatic because we didn't have continuous overlap of p orbitals. It's conjugated at all 4 carbons, but not the 5th, because we had to skip there, right? So I'm going to call this non-aromatic. Likewise with this one, we have actually only one pi system, so it's not even a conjugated one. So we still have a non-aromatic system here, because we can see there's clearly these carbons right there that are not participating in the pi system, but whoa, look at this. We've changed this carbon that was previously skipping out on the pi system to a carbon that's participating in the pi system. That lone pair can occupy a p orbital. If it occupies a p orbital, then we have every single carbon in the ring in a pi system that delocalizes with 2, 4, 6 pi electrons. And so now it's aromatic. So it became aromatic. That would suggest this is a very favorable process. Hence, the huge difference in pKa. That's why it's a much stronger acid. Much stronger acid, i.e. lower pKa. All right, there's lots of problems like that in the book and workshops, so this is an important point where we take advantage of what we know about the structure to predict reactivity. And that'll prepare you for the next chapter, which is reaction rapid fire again, like some of the old days. So, take your time to understand the structure and this bit of reactivity so that you can be prepared for new reactivity. All right, so that concludes our section on aromaticity. So I hope you enjoy that and do the homework like crazy, okay? All right, I'm gonna sign out. Farewell.